My friends, welcome back. In the last two videos, we talked about the basics of the decision trees and we talked about the math behind it and we explained it, right? With an example. So hopefully that was clear. If not, please go back to those videos and listen and watch again so that you know the basics because now we want to implement it in Python. In the previous video, we actually implemented it in Python using the scikit-learn library, but now we want to implement it from scratch, right? I'll put a link in the description for the last two videos in case you needed that. Anyway, let's get started. So I'm just gonna go start with importing the NumPy as NP, and then from collections, I want to import counter, right? And then let's bring something from the scikit-learn. So like, for example, the data sets and stuff like that. So I'm just going to go from scikit-learn import data sets and metrics data sets because obviously I want to load some data set to verify my design, and metrics because we want to calculate the accuracy. I also want to import from scikit-learn dot model selection import train test split because I want to prepare my data. And let's get started. The first thing that I need to do is to define a class named node, right? Because our tree is composed of some nodes. So what are the features of those nodes? Well, this is a class, so I'm just gonna define an init, right? And it gets self. So in each node, we need to make a decision, right? Based on like we consider the features, and based on those features we make a decision. So we need to have the feature as well. So I'm just going to go feature for now, set it to none, and then threshold, because like we want to say if feature X is less than or greater than that, right? So you need a threshold as well. I'm just going to go none for that. And then you need to specify what nodes are in the left side of it and what nodes are on the right side of it. So you need to specify the children of that node, right? So I'm just going to go left equals none and right equals none. And then obviously you want the values as well. So I'm just going to go value equals none. Okay. Well, forgot the column at the end. So basically all I want to do now is to go self.features, right? That equals feature self dot, just gonna copy this, the threshold, that equals the threshold, self dot left equals left, okay. Self dot right equals right, and self dot value equals value, right? And the other thing that we need probably for the node is a way so that we can know if you've reached a leaf node, because when we were creating our tree and we reach to a leaf node, we don't want to continue because like that's the end, right? So I'm just going to define a helper function and just call that isLeaf. Well, isLeaf node probably is more meaningful. I'd only get self, and basically all it does is that it returns self dot value is not. So instead of like having an if statement, just like the one-liner, I'm saying if self.value is not none, then like return that. So it's like basically a logical expression. Okay, cool. So we did this, and now let's define our decision tree. So I'm just gonna call that my decision tree, right? And we start with the init, so underscore underscore init underscore underscore. What is init? Obviously the self. We need some features. I'm gonna define minimum number of samples, right? Mean samples split, right? And set it to some variable. What is this min sample like? Okay, before I continue, let me explain something. The naming, it's an invention. I'm just like following the Pythonic way. Like if you open Python and if you import the decision tree from the scikit-learn library, and then like you look at the input features, and like the class definition and everything, they are using the same names. That's why I'm sticking to these names. So basically, the min sample split, that is the minimum number of samples that a node must contain to consider splitting. So basically, I'm saying if I had less than 2 nodes, then don't bother with splitting, right? That's basically all it does. Um, and then max depth, right? Let's set that to, I don't know, like 100, for example. That's obviously the depth of your tree, like how many level you want to go down, and number of features, for example, and that's none for now. Okay, and then basically we do the same thing in the initialization. So I'm just gonna go self dot minimum sample split is minimum sample split, self dot max depth is max depth, and self dot number of features, that's also number of features, and oh, we need something else too. Self dot root. We just want to say, like, we just want a way of knowing if what's the root of that tree as well. Um, okay, so this is about the init. The next thing, the next method that I want to define is the fit, right? Which we use to train our data. So it gets the self, X and Y, the training data, and then the training label. Don't forget, decision trees or supervised learning algorithms. So basically, I want to go self dot features, like number of features, that equals X dot shape 1, right? If you remember, the number of rows is the number of samples that you have, which is dimension 0, and dimension 1 is the number of columns, which is your number of features. And then we want to go self dot root equals, we probably need a helper function here, so I'm just going to go self dot underscore grow underscore tree, right? And then give it X and Y. So we will define this grow tree in a minute, right? But basically all it does is that it gets a root and like it gets the training data, and based on that training data, it creates the tree for us. So it's like growing the tree. So once we have that, let's say that we have it for now. So the other thing that we need is the predict, right? Obviously, it needs a self and some X value so that it can run the test on it and see how it works. And we can basically go return numpy that array of what do we want to do? We want to go self dot underscore traverse tree. This is another helper function that we will write. So far we have to write the grow tree and traverse tree. Traverse tree is basically like you start from the top and you check the conditions and go to different branches and eventually to leaf node to make a decision. We will implement that in a second as well. And this would obviously get an X and self dot root because it needs to know where the root is, and for X in X, right? So far so good. Everything seems to be clear. Now we have to define these two helper function that we're using. Okay, let's define them. Okay, if I go down here and say define grow tree, Okay, what are the inputs to this? Obviously self, X and Y. And then we need a way of knowing that like we're not growing too much, right? We need to keep counting the depth of our tree so that if it exceeds the max depth, so we have to stop, right? So these are the inputs to this helper function. I'm just gonna go number of samples and number of features that equals fixed that shape, right? We've seen this before, so it's pretty clear. And then number of labels, that's obviously length of numpy dot unique of y, right? So as I said before, like when you call the unique, it just returns the unique value in y. Let's say you have three classes, like you have, I don't know, like 10,000 samples and they categorize into three classes. So when you call the unique, it just gives you the three classes that you have. So length of that is just like the number of elements, which is three in this example. So this is how we get that. Okay, and now we want to grow our tree. The first step is to check if we actually need to grow it or not, right? So we have to consider stopping criteria. I'm just gonna go if, for example, depth, right, is greater than or equal to self dot max depth, we have to stop, right? This is one of the stopping criteria. The other one is that if number of labels, right, is one, right? If you only have like one label, then like you don't really need to classify anything. You just have one. Everything is in one class. And the last thing that I can think about, if it's number of samples, right, is less than self dot minimum sample split, right? Because we define that up here, and we said that like if we had less than two samples, which means one, then like it's we don't really need to classify because we know where it belongs to. So if that's the case, right, I'm just gonna go leaf value, but we know that like we have reached them to the end and we don't really need to grow our tree anymore. So we just want to return the leaf value. We just want to know what's the value in the leaf, like into what class it belongs, right? So we probably need another helper function here. I'm just gonna call that self dot underscore most common label, right? Of y, obviously. So we have to define this. Let's not forget, we have to define traverse tree. We are defining grow tree, and now we have to define most common label. So it basically looks at this list or a numpy array and returns the most common value, right? And then we're gonna return node because that's a node type, right? Node, and then we go value equals leaf value, right? So this is about that. So if this is like stopping criteria, we can actually add that in here. Stopping criteria. And if that wasn't the case, then we have to actually start growing our tree. How can we do that, right? We want to loop over all the different features and consider different threshold values, right? So that we can find the best feature. And after we found the first, like the best feature, we have to like find the condition, right? If you remember in the example that we were saying, they're saying, okay, like let's say age is, for example, the best feature that I want to use, but what's the threshold for that, right? So we want to be greedy, like we want to implement the greedy algorithm to do that. So I'm just gonna go best gain equals -1. I'm using this best gain because I want to use either the Gini impurity or the entropy metric, right, to compare all the different features. And I know those two, like both Gini impurity and entropy, return positive values. So I'm just going to start with -1. And if I found anything better than that, I just keep updating it, right? And I'm just going to go best feature right? That equals none, and best threshold, for example, for now it's none because I don't know what they are. And now we just want to go for feature index, right? In range of how many features do I have? I have number of features, right? So I'm looping through all the different features and I'm saying X column, right? That equals X of all the rows, all rows and feature index. So that specific column. So I have, all the numbers for that feature. And now that I have that, I can just go thresholds, right? All the possible threshold values, right? What are those? NumPy dot unique of X column, right? And now that I have all the threshold value, I want to loop through them to find the best threshold. So I'm just going to go for THR in thresholds, right? I want to calculate the information gain. So I'm just going to go gain equals self dot, I need a helper function here. I'm going to call that information gain, right? And it gets the Y. Yes, it gets the Y and X column, right? And the threshold. Again, if you forgot how this works, please go back to the previous videos to watch them so you understand what's exactly going on. And here I'm just saying if gain is better than the best gain, right? Then I'm going to update my best gain. Best gain equals gain. This is like a very common approach. For example, if you want to find the maximum number in a list, right? And let's say you don't want to use any of the existing functions, you can just like be like, okay, I assume the max is my first element in the list. And then if I found anything bigger than that, I'm just going to update that. So it's basically the same thing. So here I update my best gain, and then I go my best feature would be feature index, right? And then my best threshold. Oh, this is a typo here. My best threshold would be the THR, right? So we just need to calculate this, and like we need to define this information gain helper function. And now that we define that, now that we have the best feature and the threshold, we have to start growing our tree. How do we do that? So we basically need to grow the children, right? So I'm just gonna go lift indexes, right? And write indexes, right? Basically that equals self dot underscore split. This is another helper function that I want to define later. And I'm just saying basically X of all rows and best feature, right? And best threshold value, right? So basically, I will write the function that does this for me. It gets, the X values and split the data into left indexes. If you remember, I said like if the condition was true, it's the convention, right? It goes to the left. If it was wrong, it goes to the right. So I'm just gonna write a function to do that for me, and now I get the left indices and right indices. And so basically, then I want to go left equals self dot underscore grow tree. Right now that like I want to call the grow tree again on the left nodes, and then I want to call that on the right nodes as well. So I'm just gonna go call that on X of what X would that be? That would be probably left indices, right? Whatever goes there, and then y of uh, left indexes, and obviously depth uh, plus one. We want to keep like updating that, and I can do the same thing for the right children, right? I'm just gonna go right equals this will be right, and this will also be right, right? And then it's a recursive algorithm, right? See, the name of the function is grow tree, and then we just keep calling it grow tree until either one of these condition is true. So we stop, so we know that we've reached to a leaf node, right? So once that's done, we're just gonna go return. No, we're gonna return a node with best feature, best threshold, and left and right. So we need to know like what are the left and right children of that. So that's the whatchamacallit, the grow tree function. We have to write the most common label. We have to write the information gain. Let's actually start with the information gain, which seems to be an easier one. So define underscore, uh, what did we name it? Information gain. I'm just gonna copy this guy, bring it over. So it's obviously gonna have the self, the y, the x column, right? And then the split threshold, right? Uh, how do we do that? So if you remember, we can do like whatever we want here. We can calculate the gene impurity, or we can do the the other one, the entropy. Let's actually do the entropy. So I'm just gonna call it the target entropy, right? That equals, I want to define a different function as well, entropy of y, right? And I want to define this function outside my classes. So I just want to go here because like it's a very general function. Entropy of y, for example. If you remember, we have to calculate the probability and probability like pi for each of the classes that we have, and then go pi times log 2 of pi. So I just want to do that. So I'm just going to go histogram equals numpy dot bean count of y, right? And then I want to go probabilities. So ps equals hist divided by length of y, right? And then I want to return negative numpy dot sum of p times numpy dot log 2 of p, right? For p in ps, which is like all the probabilities, but only if p is greater than 0, because we don't want to have like end up with something crazy here. So now that we have the entropy function as well, we can actually call that here. So that's like the target entropy. Now we have to calculate the entropy of the child, right? How can we do that? Before actually like jumping there, we have to check something. We have to go, for example, left indices and right indices. That equals self dot. We call this, or we use the split function here, right? I'm sure we use the, oh yeah, self dot split, right? I'm just gonna bring this guy over here because we want to use that again. So we want to split our data, right? We get x call, right? And then we're going to get the split threshold as well. Okay, so we split our data, and now we want to go if length of uh, left indices is 0. If we don't have anything in the left side, or we don't have anything in the right side, then we know, right? So let's just bring this guy over. So if that's the case, then we're going to return 0 because we don't have like the gain information is 0. But if that's not the case, we want to calculate the probability of, the chart nodes. So I'm just going to go the total number of samples I have. That's obviously length of y and number of, nodes in the left and number of row nodes in the right. That equals length of this guy and length of this guy, right? So we have these, and so now that we have to calculate the entropy of each of them. So I'm just going to go entropy of left and entropy of right. That equals basically the entropy function that we have, and then that would be y of these guys, right? And basically you can copy this, and instead of left indices, we're just going to use the right indices here. And now that we have that chart or feature entropy, right, I'm just going to call that feature entropy. That equals number of, like, we need to calculate the weighted average, right? NL divided by N times entropy of left, right? So let's just put this in brackets so it's clear what we're doing. Plus, it's the same thing. I'm just going to copy this. And number of right nodes divided by N, and this would be R, right? And then we want to return the target entropy or parent, whatever you call that, minus the feature entropy. As simple as that. We have our information gain. The other function, the other helper method or helper function that we need to define is the split that we haven't defined yet. And then we had a traverse. Yes, we had a traverse tree as well. We need to implement those as well. Okay, let's get started with what do we want to do now? Defining underscore split, right? It gets the self, X column, and split threshold, for example, right? And basically, all we want to do, want to go, just want to bring the names over so we don't have to overwrite them. Left indices is numpy dot arg, where we were checking the condition, right? So takes call less than or equal the split threshold. If the condition was checked, then we go left, right? And then once we go left, we just want to flatten the data because this is easier to deal with later. And then we do the same thing for right? So if the condition was bigger than that, then do this, and then return left indices and right indices. Okay, that was easy. The other thing we need to define, and I forgot, was the underscore most common label. Did we call it this? Simulfree, Control C, Control F, this guy. Yes, so we call it most common label. That's good. So this guy is also a helper function. it gets self and y, and it's like super easy. It only returns the most common value. So I'm just gonna go um, counter equals counter y, and then basically return uh counter. I mean, so that you don't confuse that, I'm just gonna call that CNTR for counter. CNTR dot most common, right? First one, and then zero, zero. You can check out this function to see like what it returns if you want to. But basically, like with the syntax, it's just going to return the most common value in an array y. Okay, so we define most common label, we define the split, and we define the entropy, we defined row tree, and the only thing that we haven't defined yet is the traverse tree, right? So let's define that as well. So define underscore traverse tree, just to make sure that we have the yes, traverse tree. We have the same spelling. So this guy is also recursive function. It's gonna get self, x, and node, right? And basically we want to go with node dot is leaf node. So if it's a leaf node, right, we don't really need to do anything. We just want to go return node dot uh, value, right? But if it's not a leaf node, right? Let's say if x of node dot feature, okay? If that is less than or equal the node dot threshold, then we want to like extend on the left side because the condition is true. So we want to go to the left side. We just want to go return self dot we again, like it's a recursive function, so I'm just gonna call it on the left neighbor, right, or left node. So x and node dot left. And if that wasn't the case, right, which means that the condition is not true here, then I want to return the function called on node dot right. Okay. Looks good. I think we implemented everything that we needed to. We can run it, and if we forgot something, it's just gonna error out, and we can fix it later. So I'm just gonna go if underscore underscore name underscore equals underscore main. And then we want to go set a random seed, numpy that random that seed. That's like let's set it to 0. Bring our data set, data sets dot load iris, or I don't know, let's go with the breast cancer this time. Um, and then we can go return pigs y equals true. We return the values, and then we go x train, x test, y chain, and y test that equals train test split x and y, and let's go test size equals 0.2. Okay, now we have our data ready, and now we can define an object classifier, or we can just call that, yeah, just go CLF equals my decision tree. We go with defaults. We're not changing anything. CLF that, let's call our fit method with the x train and the y train values. And this is going to train it. And then I'm just going to go yped equals CLF dot predict. I'll call it x test, right? and accuracy is metrics dot uh, accuracy score of the golden result, which is white test, and the things that we calculated, which is white pred. Uh, and let's print the result. We go print f. Is it happy white test? Oh, white test. We're gonna go. Accuracy is right, and then let's go tabbing over 100 times ACC, so we get it in percentage. Percentage sign here, and then like leave it red line there, and let's run it and see if it complains or not. It's taking its sweet time now, and done. Its accuracy is like 91.22, which is pretty good. And looks like it's working. You can try that with different data set as well. You can try that with different test sizes. You can try different features, like you can limit the depth of your tree and stuff like that. And yeah, there is like a plenty you can do. A good practice for you, by the way, could be like now I implemented the information gain using the entropy metric. A good practice for you could be like writing this information gain by using the genome purity metric, right? That should be fairly easy, actually. But yeah, if you want to learn more, and I don't know, you can probably try that as well. That's it for today, and thank you for watching me. Hopefully you enjoyed it. Hopefully it was not complex enough for you guys to not to want to try it. If you found it like confusing, I highly recommend watching it again and again and try decoding yourself. Go to debug mode and look at the values of different variables to see how they're changing, and that helps a lot. Thank you for watching me, and please don't forget to subscribe to my channel to support me, and also not to miss the next video when I upload it. You guys have a good one. Take care. See you all in the next video. Bye bye.